Hello everyone. So today we're going to look at the four theories in coordination chemistry. To start off with Werner's theory, the valence bond theory, crystal field theory, and finally the ligand field theory. All of these theories are actually complementary to each other, and they actually improvise the limitations by the theory before them. The first one is Werner's theory. So Werner's theory was actually founded by Alfred Werner. The theory was actually to identify which ligand coordinates to the metal center. However, this theory was not able to justify why the difference in color occurs, and it also couldn't justify the directional of the bonding. So when there is a chemical trichlorocobalt 3 reacted or mixed with ammonia, Alfred found that 4 different colors were produced: violet, green, purple, and yellow. So the violet solution indicate the presence of 4 ammonia, and also the green solution indicates 4 ammonia. The purple color indicates presence of 5 ammonia, and while the 6 ammonia is shown by yellow. The violet and green, they are geometrical isomers. Okay, so the violet is a cis and the green is a trans. Now these different colors were not explainable. The colors was able to be justified by other theories afterwards. So when all these 4 solutions were added to them, excess silver nitrate, Alfred found that there's precipitation of white solids. And this white solid is associated to the formation of silver chloride. When adding silver nitrate to a solution of compound, and when there's precipitation of a silver chloride, white solids precipitation, it actually indicates the presence of chloride ion in the compound, in the solution. So he also found that the cis and trans, the violet and green solution, precipitated 1 equivalent of silver chloride when added excess silver nitrate. This actually shows that in the violet and green solution, the number of chloride ion that's non-coordinating ligand is 1, while the purple solution precipitated 2 equivalent of silver chloride, indicating the presence of 2 non-coordinating chloride ligand. And the yellow solution precipitated 3 equivalent of silver chloride, also indicating the presence of chloride ion, the non-coordinated chloride ion, 3 non-coordinating chloride ion. So then only, because of this observation, the new formula has now been generated. So the violet solution is now no longer trichlorocobalt 3 tetraammonia, and no longer trichlorocobalt 3 pentaammonia for the purple solution, no more trichlorocobalt 3 hexaammonia for yellow. Instead, their name has been changed according to the observation of white precipitate. Because in cis and trans, violet and green solution precipitated one equivalent of silver chloride, it means out of 3 chloride, one of them is a non-coordinating chloride. Okay, so that is the anion, the ligand that is not forming coordination within the coordination sphere, while the other 2 chloride serve as the coordinating ligand within the coordination sphere. And the rest of the ligands are ammonia, for ammonia. It is the same thing for the green solution. It's just that the violet and the green solution is distinguished by their geometrical isomers, cis and trans. The purple solution, since it precipitated 2 equivalent of silver chloride, it shows that out of 3 chloride from the raw material, 2 chloride was actually the non-coordinating ligand, the chloride ion, while only 1 served as the coordinating ligand within the coordination sphere. And the rest of the ligands are ammonia, 5 ammonia, makes the name of the purple solution pentaamine chloro cobalt 3 dichloride. While the yellow solution, since it precipitated 3 equivalent of silver chloride, it shows that all 3 chloride in cobalt chloride are actually counter ions or non-coordinating ligands, which makes the only ligand that's coordinating to cobalt is the 6 ammonia ligand, hexaamine cobalt 3 trichloride. So what is happening? Werner postulated that there are 2 valences that could explain the difference in coordination between these ligands, whether they coordinate within the coordination sphere or becoming the counter ion. So the ligand that's becoming the counter ion is classified under the primary valence. This ligand is classified under the primary valence. It is ionizable, and then this actually generates the oxidation state of the complex ion. While these ligand in blue, the coordinating ligand, are classified under the secondary valence, which are non-ionizable, like the green ligand, and these, because they are coordinating directly to the metal center, they are the coordinating ligand that contributes to the coordination number. So Werner's theory has limitations because it doesn't explain why all elements do not form coordination compounds. It doesn't explain that why not all 3 chloride can form coordination compounds, or why just only ammonia forms coordination compound, why only one of the 3 chloride forms coordination compound. It also doesn't explain the color, the different colors that's produced, the magnetic properties, and the optical properties shown by these coordination compounds. Other than that, Werner's theory also fails to explain the directional properties of bonds in the coordination compounds. So in general, Werner's theory could not explain the nature of bonding within the coordination sphere. So in summary, The Werner's theory has two postulates. One, the primary valence that is ionizable, that carries the charges, that cause the complex ion to be to have charges. There's oxidation states for the complex ions, while the secondary valence is attributed for the ligands coordinating with the metal within the coordination sphere, which actually leads to the formation of coordination number, which contributes to the number of coordination. The second theory, actually improvising Werner's theory, the valence bond theory. So in the valence bond theory, a coordinative covalent bond is formed when a filled orbital of the donor atom of a ligand overlaps with the empty orbital of the metal center. So it is always there's orbital, okay, of the ligand, let's say a p orbital or an s orbital, okay, that actually overlaps with the d orbital of the metal. There must be overlapping of orbital. The electron from the ligand cannot just jump and fill in the empty d orbital. It has to be overlapped. This is how hybridization is formed. Let's say you have a d orbital, okay, and there's a ligand. The s orbital, for example, if the donor atom of the ligand carries electron in the s orbital, that's gonna form bond coordination with the d orbital. That s orbital must overlap with the d orbital, which then actually allows the electrons to be shared or transferred to the d orbital. Okay, so this is how we get hybridization. sp, sp2, sp3, okay, combination of more than one orbital. Okay, it can be combination of the same type of orbital and also with different types of orbital. So in explaining all these theories except the Werner's theory, to explain the valence bond theory, the crystal field theory, ligand field theory, the position of the ligands in the spectrochemical series is highly important because the location of these ligands indicate the strength of every ligand. There are weak ligands and there are strong ligands, and a medium strength. It can be slightly weak or slightly strong. So this series of ligand is so important that when their orbitals coordinate to the d orbital of a metal center, will actually causes the changes in their magnetic properties, optical properties, and colors. So this series actually shows you some of the ligands that are commonly found in most coordination compounds. They are simple ligands. Well, actually, there are a lot of other ligands, slightly complex in their chemical structure, not so simple, but they carry the same principle. The halides are usually classified in the weak range ligands. The nitrate is also weak. The nitride, fluoride, they are weak. Water is also considered a weak ligand. Ammonia is weaker than ethylene diamine because ammonia is a monodentate, while ethylene diamine, EN, is a bidentate. A chelate is a stronger ligand. The higher the denticity of a chelate, it makes the ligand much stronger. The nitrate, phosphine, cyanide, and carbon monoxide, these are among the strong ligands, but the cyanide and carbon monoxide are the strongest among all. So this series is going to be a very important point when discussing why some coordination complexes that initially look like as if they are paramagnetic, but when they are actually diamagnetic and vice versa. Okay, let's see what valence bond theory explains about the hybridization, the bonding of ligand and metal, because Werner's theory was actually not able to explain the bonding. So valence bond theory explains that when there's bond, coordination, covalent bond, coordinative covalent bond, there must be hybridization between the orbitals of the donor atom that carries the electrons with the empty d orbital of the metal center. Now, let's say we are going to look at the coordinative compound of iron 2. Now, the electronic configuration before 4s2 is actually the same. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so we don't actually focus on that because those are the inner shells. Okay, the inner shells electrons that do not participate in the formation of bond. We only focus on the configuration that participates in the generation of chemical bonding. So the iron configuration here is 4s2, 3d6. When iron becomes iron 2 plus, the 4s2 is removed. The 2 electrons in 4s is removed, leaving the 4s empty with only 6 electrons in the 3d orbital. So if you draw the iron configuration, it will look like this. We always draw the 4s first. Okay, fill in the 4s first, and then followed by the 3d. So an iron 2 will have both electrons in 4s removed. Now, if iron 2 is going to react with cyanide and water. Now from the spectrochemical series, cyanide is the strongest ligand, just like carbon monoxide, while water is a weak ligand. Not the weakest, but the weak ligand. Not as weak as the halides, but still within the weak range ligand. So cyanide contributes 2 electrons. So how does this hybridization occurs? Okay, so this is your iron 2 electrons. Okay, iron 2 electrons. Cyanide is a strong ligand. What is defined by strong ligand? It means this ligand is able to force any unpaired electrons in the d orbital of the metal center to pair up. Now you see iron 2 has 1 paired electron and 4 unpaired electrons. Okay, there's 1 paired electron and 4 unpaired electrons. When these iron 2 plus reacts with cyanide, cyanide being the strongest ligand, cyanide is able to force every of these unpaired electrons to pair up. So what happened is, before the hybridization occurs, these electrons will be pairing up. Okay, they will pair up. So what happened is, that will happen, right? When that happens, there will be 2 empty slots in the d orbital of iron 2 plus. Now you see there are 6 cyanide, where every cyanide ligand contributes 2 electrons. Now, in which orbitals would these electrons occupy? The cyanide will start occupying the empty 3d orbitals. Here, 1, this is from 1 cyanide, this is from the 2nd cyanide, this is from the 3rd cyanide, this from the 4th cyanide, this is from the 5th cyanide, and this is from the 6th cyanide. So do you see any unpaired electrons? No, there's no unpaired electrons. Everything is paired up. It makes this complex here a dimagnetic. So this complex is a dimagnetic. Okay, a dimagnetic, because there's no unpaired electron. Is this complex hexacyanoferrite 2? This is ferrite 2 plus. Is this ferrite 2 plus? You have ferrum 2 plus and 6 cyanide. So the overall charge is -4. So hexacyanoferrite 2 plus, is the hybridization produces it, is the hybridization is an inner orbital hybridization or outer orbital? This is an inner orbital. Why is it called inner orbital? Because the ligand is filling up the empty spaces of the d orbitals that belongs to the metal. Now, how about this? How about when iron 2 plus reacts or coordinate with water? Now again, this is iron 2 plus configuration. Okay, so the iron 2 plus configuration has 1 paired electrons and 4 unpaired electrons. When coordinate with 6 water, every water molecule will contribute 2 electrons. But since water is a weak field ligand, it won't be able to force these to pair up. It won't be able to do that. So what is going to happen is the electrons contributed by water will start filling in the 4s orbital. Okay, so this is the first water, that's the second water, third water, fourth water, 6 water, 5th water, and 6th water. Do you see any unpaired electrons in this hybridization scheme? Yes, there are 4 from here. All right? So it makes this complex a paramagnetic because there is a presence of unpaired electrons. Is this an inner orbital or outer orbital hybridization? Since the electrons contributed by water does not fill in the empty spaces of the metal's d orbital, instead it fills in the 4s orbital onwards. It fills in the 4d orbital and not the 3d. So this is known as the outer orbital hybridization. It's an outer orbital hybridization. Okay, when it is supposed to fill in the 3d orbital, but because water is a weak field ligand, it couldn't force the unpaired electron in iron 2 to pair up. So it started to fill in starting from the 4s up to 4d. So this is an outer orbital hybridization. So what is the hybridization of iron 2 with 6 cyanide? This is D2. Why is it D2? Because cyanide takes 2 orbitals from the 3D, uses 2 orbitals from 3D, so D2. This is S from 4S, and P. How many P? 3. All 3 rooms in 4P is used up. So the hybridization is D2sp3, and this is inner orbital hybridization. Whereas for iron 2 with water, the hybridization is S. It doesn't start with D because the electrons in water does not fill in the 3D orbital. It starts with S and then P. How many P orbitals are used up? 3. And then the d orbital from 4d. How many orbitals are used? 2. It's sp3d2. This is an outer orbital hybridization. Both of them give the same coordination number, 6 coordination number. Both of them are monodentate. Both of them coordinates through one donor atom. Both of them gives an octahedral geometry, but in a different hybridization approach. One is inner orbital because of the properties of the ligand being a strong ligand. One is giving the outer orbital hybridization because of the nature of the ligand, water being a weak field ligand. Let's look at other example. For example, if we have zinc, okay? So zinc, the electronic configuration involving 4s and 3d is 4s2, 3d, 10. Zinc at its ground state configuration is 4s2, 3d10. Zinc 2 plus will remove 2 electrons from 4s, leaving 10 electrons in the 3d orbital. So this is that is the wrong way to fill in. The right way is you have to fill in every orbital with a single electron first and followed by completing the orbital. Okay, so the 3d orbitals in zinc 2 plus is fully filled up. Now, if there are 4 chloride ion to coordinate with zinc 2 plus, what kind of hybridization this will make? Chloride is a weak ligand, much weaker than water. So as a weak ligand, weak field ligands are not able to force electrons in the metal's d orbital to pair up if there is or there are unpaired electrons. If the metal's 3d orbitals does not have any unpaired electrons, so there's no activity for pairing up electron will happen. This will make the ligand start filling in the 4s level because the 3d orbital here is already fully filled. Okay, so there's no more option for chlorine. Even if a strong ligand is used, it will still fill up the 4s orbital because the 3d orbital is already full. A strong ligand will not break the paired electron to unpaired electron. Okay, the strong ligand will only force the unpaired electron to pair up, not breaking the paired electron into unpaired electrons. So this chloride, every halide contributes 2 electrons. Since there are 4 chloride, there will be 8 electrons contributed. So it starts with 4s. 1 chloride, 2 chloride, 3 chloride, 4 chloride. So this is, the hybridization is sp3. A tetrahedral. Is there any unpaired electron? No. It's diamagnetic. Okay? The absence of unpaired electron will make the coordination compound, the complex, diamagnetic. What if a strong ligand is used? A strong ligand. Okay, remember, because the d orbital is already fully filled, even if the ligand is strong, the ligand will not force electrons in the d orbital to pair up because they are already pairing up. So the strong ligand will also start filling in the 4s orbital and use the 4d orbital if needed. This actually leads to the difference in magnetic properties that can be measured via magnetic moment. The magnetic moment carries a symbol mu. Okay, mu. What is magnetic moment? Magnetic moment is a measurement that is determined by the presence of unpaired electrons in the metal center, d orbital. Because the number of unpaired electrons in the metal center, the d orbital of the metal center, will result in whether the complex is a diamagnetic or a paramagnetic. So if there is a presence of unpaired electrons, the complex will become paramagnetic because the complex, the unpaired electron will align themselves, will respond to the magnetic fields around them. Whereas if the complex does not have any unpaired electrons, these unpaired electrons repels repels against the magnetic fields around them. Ferromagnetism is also about having unpaired electrons aligned in the same direction with the magnetic fields. But usually, we'll see the ferromagnetic properties in compounds not for coordination compounds, usually alloys, pure metals, they can show ferromagnetism. Coordination compounds usually shows paramagnetism. So how do we measure the value of magnetic moment? This is the formula. Okay, so it's actually mu equals to n times n plus 2, and there's a square root. Okay, so n times n plus 2 square root. N is the number of unpaired electrons. That's why for diamagnetic compound, the magnetic moment will be 0 because there's no unpaired electron. So the N is 0. The unit for magnetic moment is Bm. What is Bm? Bohr magneton. Okay, Bohr magneton. So the number of unpaired electron plays a crucial influence in the value of magnetic moment. At least one unpaired electron present in the d orbital of the metal center will generate paramagnetic properties. Then the higher the number of unpaired electrons, the greater the value of their magnetic moment. So if you see a value for magnetic moment like 4.89, 5.5, it means that the number of unpaired electrons in the d orbital is high. For copper 2 complex, because copper 2 complex has only one unpaired electron in the d orbital, the magnetic moment measurement usually around 1.73 or 1.79. So the limitation of valence bond theory managed to explain magnetic properties, but it actually did not explain very well how different colors are given by complex ions and what caused the high spin and low spin phenomena in coordination compounds. High spin means more unpaired electron. Low spin means high spin, low spin. Yeah, low spin means low number of unpaired electrons. Spin here refers to the electrons. Usually when the ligand is strong or weak, when the ligand manage to force the electrons in the d orbital, the metal's d orbital to pair up, it actually promotes to generating more paired electrons. So that's why the number of unpaired electron is not so much, not so great. Okay, so that will fall under the low spin class. While the ligand, if it's weak, the ligand is unable to force the metal d electron to pair up. So this will leave the electron as it is, unpaired electrons, and that will be classified under high spin. Well, this can be explained by crystal field theory later. Okay, so valence bond theory explains the hybridization, how bonds are formed. And explain the magnetic properties, why some coordination complex are diamagnetic and why some are paramagnetic. So that's all for today. We will continue with crystal field theory and ligand field theory afterwards. So by this list of compounds and try to show the bonding by drawing the hybridization scheme, and from there you will be able to determine whether these complexes are diamagnetic or paramagnetic, and this will also lead you to the measurement of the magnetic moment, because the n value, which is associated to the number of unpaired electron, are given when you draw the hybridization scheme. So there are lists of compounds A until J. There are different kinds of ligand, from the strong and weak field ligand, and different oxidation state of metal. Okay, so please try this and see me if you need help.